All right, lesson 9-3.3, relative rates of growth. We're gonna we're gonna get weird, but not horribly so. This is really not that challenging to understand. You can use L'Hopital's rule to solve a lot of these problems, but what's going on here? All right, well, which one grows fastest? All right, we're restricting our discussion of functions that stay positive as x goes to infinity, but it doesn't really matter. There are four. I'm only going to show three to start. A log, with some base. A x to the n. Now this is a linear one, but it could be to any power. And then an exponential, which is an a to the x, often given as e to the x, because that's the one we're most fascinated by. Okay, sure, whatever you say. Which one grows fastest? Well, clearly a to the x grows fastest, x to some n goes second fastest, and then log grows the slowest. And log really does grow very slowly as it gets further and further out. It takes a long time for things to accumulate. So why do we care? Well, I'll get to that. This is going to be used in Unit 10 to see if a series will converge. But they want you thinking pretty good about that in AP Calc. The one function we're not talking about is a factorial. Later. That one grows fastest of all. Anything with an n factorial on the bottom is gonna converge. That's Unit 10 talk. So you don't need to worry about this now, but it's not a bad idea. If this was in class, I would probably show people a little bit more about what I'm talking about. So here's two functions, f of x and g of x, and we say, if x keeps getting bigger and bigger, sufficiently large, which is like what? Meaning it works. If we get infinity, then f of x grows faster. Upside down, we'd get 0. And then, and g grows slower. We can say that. Take derivative if we are not sure what's going on using L'Hopital's rule, so on and so on. Now we get a little weird. If they grow at the same rate as we go to infinity, we get some value L. Typically not 1. One's a special case. Talk about that in a second. All right. And this is one of those lessons you're like, okay, I don't know why you're getting into this, but sure, whatever you say. Let me show you. So which grows faster, 2 over x or x? So we do it as a limit. Say limit as x approaches infinity, and we put one on top of the other. Which one? Doesn't matter. If it goes to infinity, top's faster. Goes to 0, bottom's faster. Top heavy, bottom heavy is very commonly used. I actually don't use it that much, even though I kind of like it. I don't know, it just doesn't pop up. X's cancel, we get 2. So we get 2. That's that L thing we just saw on the previous page. We would say they grow at a constant rate. Which you say, no, they don't. That's x and that's 2x. Look, as they get bigger and bigger, they diverge. That's not what we're getting at. That's not what we mean. All right, their growth is at a constant rate. I have no idea what I wrote here. That's very weird. So strange. Oh, I wrote grow at. That's funny. Growth is at a constant rate. Well, it's my stupid handwriting. All right, so that's what they're getting at. All right, they are growing at a constant rate. You could argue that the growth between them is growing at a constant rate. It's not taking off without the other one having any idea where it's going. Get used to that. But what if L equals 1? Then we use this weird little expression. Each function, and again, we're on positive, is the right-hand behavior. We often write RHB, right hand end behavior of the other function. Let me skip ahead in my notes and show you what I'm talking about. And I will come back to these. All right. So you've got x plus sine of x and x. Here's your two functions. All right, so again, we do a limit thing. All right, they're both going infinity. All right, let's L'Hopital's rule it. Derivative of x is 1, derivative of sine of x is cosine of x. Actually, we're not going to do that. We can do it a different way. So we're not doing L'Hopital's rule. We're going to distribute the x. So we get x over x plus sine of x over x. All right, we end up getting, this goes to 1. This goes to infinity, so we L'Hopital's rule it. We get 1 over 1. All said and done, we get 1. Meaning they have the same right-hand end behavior, meaning the sine of x just kind of wobbles around. As we get out to infinity, x gets really, really big. It's just like x. That's what they mean by right-hand end behavior. More as we go along. By the way, we jumped a little bit there. So that's how we compare things using L'Hopital's rule. All right, so let's see what's going on. Which one do you want to put on top? I like going to 0, so I'm going to put the x squared on top. You can put either one, it doesn't really matter. And we get infinity over infinity. You say, I don't know which one grows faster. Well, let's L'Hopital rule. Nope. Really should put my limit in here. 2 over e to the x is 2 over infinity, which is 0. All right, so you can say that e to the x grows faster than x squared, which is what I showed on the original graph. How about ln of x and x? Limit x approaches infinity, ln of x over x, infinity over infinity. L'Hopital's rule, x approaches infinity, 1 over x over 1, which is the same as 1 over x. As we go to infinity, we get to 0. Therefore, x grows faster than ln of x. For x squared, we get infinity over infinity, which we do calculus to. I put x squared on top of my example, that's fine. X goes to infinity, 1 over x over 2x, which is the same as x goes to infinity of 1 over 2x squared, which is 0, which says that x squared grows faster than ln of x. I could easily do this with the 2x squared on top and say it goes to infinity, which means x squared goes faster than ln of x. Well, it just needs practice. Okay, let a and b be numbers greater than 1. Well, that just means we're not doing something ludicrous with our logarithms. So show that they grow at the same rate. Now, this is like the 2x and x I did earlier. They're like, well, no, certain logs are going to grow faster than others. No, we consider that the same rate according to the math we're doing. So limit x approaches infinity, log base a of x, log base b of x. Hey, they both get really big eventually. Fine. Limit as x approaches infinity, ln of x over ln of a, ln of x over. That doesn't feel right. I don't know where I'm getting ln of x. Let's fix that. 1 over x ln of a. 1 over x ln of b. Weird. I hate it when I make mistakes in my notes. Flippy floppy, yada yada. Ln of b over ln of a, which isn't 1, is a constant, which means they grow at the same rate. All right, remember what it said. Back to our rules. Same rate if they approach some L, which stinks. People don't like it. Yeah, well, welcome to the party. So growing at the same rate is transitive, if you remember that. A is greater than B, B is greater than C, A is greater than C. That's your transitive property in case you've forgotten, which I wouldn't blame you if you had. So show that they grow at the same rate as x approaches infinity. I'm really not in the mood for this, but let's see what we can do. Limit as x approaches infinity of root x squared plus 5 over 2 root x minus 1 squared is infinity over infinity. So we go, well, now what? We take derivatives and all that nonsense. Doesn't necessarily help. So, hey, let's bring in this. This is stupid. I would just do my calculus, but whatever. Let's bring in some h of x equals x and try that one instead. So let's do root x squared plus 5 over x. All right, before we do calculus, I'd shove it in there as an x squared. So it's a x squared plus 5, and I'd distribute it. So we are still there at 5 over x. Oof, oof, oof. Don't like it when my handwriting goes glitchy. Infinity gives me 0, gives me 1. Oh, what do we say about 1? I don't know, I can't remember. That's why we write things down. Then each function is the right hand end behavior. So they're basically the same function. All right. I can do that again with this one and get the same thing. Be aware. Yes, this one's like x. So well, let's do it. So then limit x approaches infinity. Doesn't matter which one I put on top, but that's how I like to do it. Let's see. Again, I'm going to do this with algebra. I'm going to write this bottom as root x squared. So then I can shove it all together. And distribute the root x. I can't now because I wrote it like an idiot. So limit as x approaches infinity. 2 root x over root x minus 1 over root x squared. See ya. As it goes to infinity, we get 2 minus basically 0 squared, which is 4. Which means, if I recall from my earlier notes, they go at the same rate. Don't have the exact same right hand end behavior apparently, but they grow at the same rate. That's it. That's it. I'm done. I got nothing else to add. This is kind of a prep lesson for those who are like, I kind of got it. I don't know what the hell you're doing that for. We'll get there. We're going to build on this, so be prepared.